Welcome back, guys and gals. We are still in our functions unit, believe it or not, but we're going to take sort of a weird turn. We've talked about slope. We've talked about y-intercept, graphing lines, finding equations, all that stuff. Today we're going to take a hard turn here. We're going to talk about something called a scatter plot. Now, you should be somewhat familiar with it. We're going to do this in two parts. And we're going to talk about what scatter plots are, how to sort of read them. In our next lesson, we'll talk a little bit more about reading them and what we're ultimately going to do. But just trust me on this. We're going to deal in scatter plots, and let's make it real clear, a lot of scatter plots are not functions. So get that out of the way. So real quick, just a quick reminder in case you've never dealt with scatter plots before. What is a scatter plot? Well, quite frankly, it's a graph that we'll create with bunches and bunches of little dots all over it. And what it does is it graphs two sets of data to see how they relate to each other. In other words, we want to see if there's something going on between our two sets of numbers. All right. The two sets are combined to create ordered pairs. All right. One data set is going to be considered the independent variable, and then the other data set will be considered dependent. For example, here's two sets of data. I grabbed some random folks and found some measurements on them. I looked at their arm span in inches. So I measured from fingertip to fingertip, and here they are. And then I also measured their heights standing up from the top of their heads to the bottom of their feet and put this together. So here's two data sets. I'm going to pretend that arm span is going to be my x variable, all right, independent. And that means height would be dependent. So here's what I'm thinking. I think that if I know a person's arm span, all right, again, from fingertip to fingertip with arms stretched out, that I could then see what their height would be without actually measuring their height. And that's what our scatter plots are going to try to do. They're going to see how well related these two items are. And as it turns out, arm span and height are fairly closely related. So let's talk about how we're going to put this together, and then we'll look about how we read it. Right? So the first thing we need to do is label things. Arm span we said was going to be x, so here's our x-axis. We always want to label what's going on. So I'm going to label this as arm span. By the way, you'll notice that I'm working with a pencil today. I'm doing that because making mistakes is going to happen on this. So I'm going to try and steer clear of using my pen and using a pencil. I strongly recommend you do as well. So arm span being measured in inches, so let's label that. We said our y was going to be height measured in inches. And then typically, not only are we going to title our x and y axis, but we try to title the graph as well. So in this case, I will say arm span versus height. All right, just to give the reader an idea of what we're looking at. So the hardest part of putting these together is creating what we call a scale. Right? In other words, how I'm going to number off the x and the y axis. Notice my numbers here in my x. They don't go all the way down to 0. So here's what I wouldn't want to do. I don't want to number this off, say, 0, 10, 20. I don't want to do that because notice most of my data lies from about 60 up to the mid-70s. Well, and if I did that, let's carry on, 30, 40, 50, 60, 70. Most of my data would sit right in here and everything else would be blank. So here's what we want to do. You want to look at your data, try and figure out what is the smallest number, so in this case about 60, and then what is your largest number, so in this case close to 80, and we want to make our scale fit that range, so we can kind of tease the data out a little bit. Well, and if we're going to do that, we're going to want to keep each box measuring the same amount. Well, that means we're going to make a jump. I'm going to jump from 0 up to, say, 50, and then after that I'm going to count by a different amount. To do that, here's what we're going to do. We're going to put a break. It's a squiggly line in there to show that we've jumped. We've gone from 0 in this case, and I'm going to start maybe at 50. So we'll let this first tick mark here be 50 inches. And then after that, I'm going to count by a new measure. So from here to here, this box measures 50 inches. And then after that, I'm going to let maybe every 2 or 3 boxes count for 10. So let's try that. I'm going to count 1, 2, 3. So there's 60. 1, 2, 3. There's 70. 1, 2, and then 3. Somewhere in here would be 80. So notice I've spread that out, each set of boxes, so in this case, roughly every 3 boxes is 10, but this is only 50 for 1. So that break tells me I'm counting by something different here, but by another amount once I get beyond it. Cool. So we got that. Let's look at our Ys. The Ys have an even closer span. Instead of getting the 50s, they only go from the 60s up to mid-70s. So I'm going to put a break in. So again, 0 up to my first mark. And in this case, since 61 is the smallest, I'm going to go ahead and start at 60 here. Count up 1, 2, 3. Yeah, we can do that, 70. And then 1, 2, 3, 80. So that way it's going to spread our data out a little bit. So let's start plotting. So these are ordered pairs. So 76.5 is my first one. So let's go over here. 75 is about midway. So I'm going to go just a hair over. And then up to 75, that's about here on the Y. 76, we'll call it about here. So notice, 75 is midway. We're going to go a little over. Again, 75 is a little midway. We're going to go over. So about there. All right, let's try it again. 69.5. So 69.5, really close to 70, and then we're going to go up to about 71. I'm going to call it there. So notice with these, we're going to have to get as close as we can. We're not going to be able to be exact, and that's okay, but we'll try to be as close as we can. All right, 62.5, so maybe somewhere in here, on up to 62, so I'll put that maybe, I don't know, about in there. 61, so a little bit further over, but still at 62, so maybe in here. And then 59, so we're going to go just to the other side, and it's at 61, I don't know, somewhere in there. All right, looks good. So now we've got our scatter plot. All right, notice that our dots seem to want to group together. And what we're looking for as we read our graph is we're looking for something called correlation. At least that was the word we used when I was in school. Now the word that they want to use is association. And here's what it means. Correlation is simply another word for a pattern. What patterns do we see? All right. And there's different patterns. So here are some of the ones that we're going to look for. One is called positive correlation. In other words, that if I look at the data, it tends to kind of group together and it tends to want to go upwards. All right. So this definitely has positive correlation. In other words, the data seems to want to go upward. All right. Whereas negative correlation would say maybe go like this and trend downward. But notice this tends to want to go up, so it's definitely positive. We can also talk about the data being linear. In other words, it tends to want to follow a line. So I'm going to grab a different colored pencil here. Linear correlation means that if I were to draw a line, so grab a straight edge here, I could draw a line somewhere through my data, I don't know, maybe about here. I'll just sort of eyeball it. And notice how my data, if I keep it straight, seems to want to follow this line. Now, is it perfect? Are all my data points on the line? Absolutely not. But notice how it tends to want to follow that line. So in this case, we not only have positive correlation, but we also have a linear pattern. So we call it linear correlation. All right. We could also have nonlinear correlation. So that would mean maybe our dots form a curve. Maybe it's an up and down, or maybe kind of a zigzag, but that it follows a distinct pattern that just happens to be nonlinear. Last but not least, there is no correlation. In other words, the dots are just random on the page. There's no real pattern for us to discern. So today, what we're going to do is we're going to focus on making the graphs, all right, making sure we're getting them exact, labeling things, and then identifying that correlation, in other words, those patterns that we see. So in this case, if I were to describe my graph between arm span and height, I would say that there's positive correlation. Notice, as a person's arm span gets larger, notice their height also tends to get larger. So if you have a larger arm span, I could predict that you would have a taller height. So if I knew somebody with, say, an 80, good grief, that would be huge, an 80-inch arm span, well, then I could predict that, yeah, they're probably going to be close to 80 inches in height as well. Now notice, it's not perfect, but it's close. I also notice that it's linear. So that way, everybody's going to follow that same basic pattern. If, let's say, your arm span goes up by an inch, then maybe your height also goes up by an inch, and so on. So that's what we're going to do today. Make the graph, and then talk about, well, what are we seeing, and how are we going to read those graphs. So let's try a few more here real quick. All right, this one. I've got the altitude of a skydiver. So what we did is we tracked that individual's time after they left the plane and then their height. So we just used an altimeter to see where they were in time. So let's start with the x-axis. In this case, I know it's going to be time. Time almost always is x. So we'll put this as time in seconds. In this case, they're falling at a pretty quick clip there. And let's be clear. This data is not 100% exact. You would reach something called maximum velocity, and you wouldn't just keep falling faster and faster and faster. But again, we're going to ignore the physics for the time being. So time, in this case, it's 0, 5, 10, 15. So what I'm going to do is I'm going to count every 2 boxes for 5. So the 5-second mark will go here, count 2 boxes, 10, count 2 boxes, 15, count 2 boxes, 20. And notice that spreads our data out fairly well. It's not all going to be scrunched down here. I wouldn't want to count 5, 10, 15, 20, because then all my data would simply sit here. I want to spread it out. All right, well, let's look at height. Goodness gracious, the height that this skydiver is above the earth is quite a range. It goes from 10,000 up here all the way down to 3,600. So what I figure we'll do is we'll count, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, almost 10, we'll call it. So what we'll do is we'll count every box as 1,000. And I'm not going to write 1,000, 2,000, that gets boring. I'm going to skip. So this is 2,000. Then skip, this is 4,000. Skip, 6,000. So again, my scale is going up by 1,000 every box, but I'm only going to write in for every other. 8,000. And then, of course, up here, even though there isn't a line, we know it's there, and that is 10,000. Excellent. All right, well, let's start. Oh, we forgot our title. So we could say Skydiver, so we'll call it Skydiver's Fall. All right, there we go. So at 0 seconds, our skydiver was at 10,000 feet, and I'm assuming that's when he or she took a leap out of the plane. So we'll come up here, we'll make our first data point. That one was very easy to spot. All right, 5 seconds in, so 5 seconds in, they're at 9,600 feet. So let's get up here. 9,000's here, 600 is very, very close to 10, not quite, but close. So we'll put it there, all right? 10 seconds in, all right? So 10 seconds have passed. They're at 8,400. So let's see here. There's 8,000, that's 9,000. 400's kind of in between, so I'm going to put it about here. All right, looks good. 15 seconds. So let's see, 15. Here we are, 15 seconds in. Now they're at 6,400. All right, let's get up there. 6,000, that's 7,000. So 400's, I don't know, it's about in here. Make it, that looks good. And then 20 seconds in. Let's see, 20 seconds, it says it's at 3,600. So let's see, 20, there's 2,000, 3,000, 4,000. So 3,600, I don't know, about right there. Cool. So there's our data, all spread out. Now, one thing I noticed that I'm going to grab a straight edge here, if we're talking about possible linear correlation, is that I'm noticing my data points really don't seem to want to follow a line. You know, I could try to line up a few points, but then there's always seems to be another point that's not quite meeting up with it. So in this case, I would definitely say that I have non-linear correlation. All right, definitely doesn't look linear. We seem to be going in a curve. All right, and that makes sense because when you fall, it's not a linear just drop. You go faster and faster and faster and faster. All right? Notice, so we're nonlinear. I also notice we're not positive, right? Positive correlations like this, trending upward. Well, in this case, we're losing altitude, so we are trending downward. So this is definitely also negative correlation. Now, instead of writing nonlinear and negative correlation, we could simply say we have negative nonlinear correlation and get it all in one go. But that's what we're doing today, all right? We graph the situation, we look at it, and see what's happening. And again, it should make sense. The bigger the arm span, taller the person, cool, that makes sense. A skydiver, falling, yeah, they're going to be losing altitude over time, so it's definitely negative. As this number gets larger, this other number gets smaller. And it being nonlinear, yeah, that makes sense. You're not falling at a constant rate when you jump out of an airplane. You're going to go faster and faster. Let's try another one. One I definitely want to show you is this one. I like this one. All right, pets to siblings. All right. So what we did is we asked a number of people how many pets do they have, and then how many siblings that they have. Right. And I just grabbed some random people and asked the questions. So some people don't have any pets, obviously. I had one person tell me 8, and then the number of siblings that they happen to have in their home. So let's take a look. In this case, we're going to let number of siblings be X, and I'm going to see if I can take the person's number of siblings and accurately predict, or excuse me, number of pets rather, and then accurately predict the number of siblings. So the x-axis is the number of pets. And notice this goes from 0 all the way up to 8, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 9 lines, so I'm just going to count 1 for each, but I will go every 2 boxes. So 2, 4, 6, 8. And again, that just keeps it from being so cluttered. Number of siblings, I've noticed, we go from 1 all the way up to 5. It doesn't look like we had anybody that was an only child, which is odd. There's usually at least 1, but that's fine. So we'll write on the side here for this number of siblings. All right? And since we've got 10 sections there, I'm going to count every 2 boxes for 1. So we'll skip to 1, skip to 2, skip to 3, skip to 4, and then all the way up here would be 5. All right, cool. And then for a title, I don't know, maybe we just call this pets versus siblings. I don't know. It works. So let's start plotting. So this person had 0 pets, and they had 4 siblings. So we'll go up here and we'll make a mark right there. Right? 0 pets, 4 siblings. This person had 0 pets and had 3 siblings. All right, so we'll mark them there. 1 pet, and they had 5. So 1 pet and 5 all the way up here. 1 pet and 1. All right, so 1 pet and 1. 2 pets and 5. So 2 pets and 5. 2 pets and 4. 2 pets and 4. All right, 3 pets and 1. 3 pets and 1. 5 pets, we're going to go over here, and 5. And then 8 pets and 4. There it is. So let's talk about correlations. All right, let's look. We'll go back here and we'll get our list so we don't miss anything. And I'll fold it in half. Take a look. Let's look at our correlations. Do we have positive correlation? Well, if I take a straight edge and try to see if it's trending up, that really doesn't seem to work. If I try to draw a line through here, all right, well, let's try negative. Maybe it's going down. No, not really. And even just side to side, that doesn't seem to want to work. All right, linear. Maybe we can see if we can get that line in. Maybe, I don't know. Not really. Let's try nonlinear. Maybe there's a curve we're not seeing. I'm not really seeing it. So here's the deal. If it's not going up, not going down, we can't see a line that's developing. We can't see a curve that's developing. No discernible pattern. Then what we say is that the data has what we call no correlation. In other words, there doesn't seem to be anything going on between the data. And that makes sense. The number of pets a person has really may or may not have any bearing on the number of siblings. For example, in our house where I live, my children have the 2 of them. I just have 2 children, so they have each brother, so 2 siblings, or 1 sibling each, 2 of them together. And we only have 1 pet. We have 1 cat. So if I were to ask my oldest son, how many siblings do you have? He would say 1. And how many cat? 1. And that would be it. But growing up, I had multiple pets. I had 2 cats, a couple of fish, but I also only had 1 sibling. So I would have been up here. So notice, my oldest son and I have the same number of siblings, but very different numbers of pets. So again, it's going to be sort of interesting to see how some of these different data sets will play out. Whereas my number of pets is over here, his number of pets is here, though we're the same siblings. So if you see no correlation, it means, well, there's really nothing going on here that's to speak of. Pets really don't have anything to do with siblings, and that's sort of to be expected. So today, as you're working, a couple of things. First, make certain you know what's independent and dependent, all right, because you don't want to get them backwards. Second, make certain that your scales make sense for your situation. We don't want all of this data in one teeny tiny spot. Notice here I did not need a break, whereas in some of our original work, we did put a break in to recognize that from here to here is 50, but then after that, every 3 boxes is 10, to show that we're not counting by the same amount here. On this one, we did. Every 2 boxes counts for 2, or every 2 boxes counts for 1, so no need for a break. So scale, breaks, make sure you're labeling everything and that all your points are in the right spot. Some are easy to plot, like this one, obvious to put them in the correct spots. Others may be more difficult, right, to get exact. Just try to be as close as you can. And then last but not least, as we go through things, describe it, right? What sort of patterns do you see? That's basically the gist of correlation. Sometimes you'll see no pattern, and that's okay. Sometimes you'll see the pattern where things are trending upwards, so that's positive. Or they follow a line, so it's linear. Maybe it's trending downward. And in this case, if I were to draw the curve in, let's see here. Yeah, it's following a curve. Yeah, I mean, that's almost perfect. So definitely nonlinear and definitely negative. All right, so that's what we'll be doing today. So again, pencils are key. Do not bring a pen. And we'll try some of these together and see what we can do. All right, y'all have a good day, and we'll see you in class.